This is part 2 of the Module 5 Problems for Students. We'll pick up where we left off. What's the mole percent of ethanol, C2H5OH, in 180 proof vodka? And they give us the composition of that solution, 71 grams of ethanol and 10 grams of water. Okay, we don't really need the proof number here. It's an interesting cultural reference, but we don't have a way to, there are ways, but we do not have a way in this course to use that number to get us any useful information. What we do have, though, are the amounts. So mole percent, that's the same as mole fraction, but we just put it in a percent format instead of the decimal format. Okay, let's assume that we have 81 grams of starting material. Now in the past, I've said let's start with 100 grams because we didn't really have any other basis to start with. Here we have the 71 grams of ethanol and the 10 grams of water. So it makes sense to add those two together, get 81 grams, and let's just use that as our starting material. We could use 100, but then we'd have to do a little bit of arithmetic to get what the numbers would be for ethanol and water. 81 just sort of cuts out the middle step. So let's convert these amounts to moles. Well, that's pretty straightforward. We take our 71 grams of ethanol. We know the formula for ethanol because they give it to us in the problem. The molar mass is 46.08. We get 1.541 moles of ethanol. We do that for water, 10 grams divided by 18.02. 0.555 moles of water, and then we just do a mole fraction problem, only we're going to call it percent. We're just going to multiply by 100 at the end, so we get a percent instead of a decimal number. So we take the moles of ethanol, which is 1.541, divided by the total amount of all the moles, which would be 1.541 plus 0.555, that number comes out to be 0.735. We convert that to a percent by multiplying by 100, get 73.5%. So our answer is A. All right, next problem, we're going to shift over to the material which is not in the book, but which we talk about in class. We're going to calculate the molar mass using Raoult's law. All right, the problem says when 8.05 grams of an unknown compound, and we're going to call this compound Z, it doesn't matter what you call it, it's dissolved in 100 grams of benzene, the formula for benzene, C6H6. The vapor pressure of the benzene decreases from 100.0 torr to 94.8 torr. What's the mole fraction of the solute? And then what's the molar mass of compound Z? Again, looks like a hard problem to solve. Raoult's law says that the total pressure is the sum of the partial pressures of all the components. In our case, we only have two components, so we'll call those A and B. And A and B pressures come from the mole fraction of each of those times the vapor pressure of the pure compound. That's the P sub A with a 0 superscript. All right, so what have we got? X, or chi, is the mole fraction. P0 is the vapor pressure of the pure liquid. A and B are the two components. But we have just one component that we know the numbers for, okay? So we could say that the P solution then is going to be the mole fraction of the solvent times the vapor pressure of the pure solvent, because that's all we know is one compound or one component. Let's rearrange that. If we solve for the mole fraction of the solvent, we just divide both sides of our equation by P solvent. And now we have two pieces of data that we actually know. We know P solution is 94.8, and we know the pure pressure is 100.0. So we get 0.948, and that's the mole fraction of benzene. Therefore, the mole fraction of the unknown compound must be 1 minus the mole fraction of the benzene. So we can do that subtraction and get 0.052. Now, we also know that moles is just grams divided by grams per mole. So we can write this equation for mole fraction to allow us to calculate the unknown molar mass. Okay, so we have benzene, which would be 0.948, and that's our mole fraction. That's equal to 100 grams of benzene, which is given in the problem, divided by the molar mass. And then in the denominator, we've got to come up with the number of total moles. Well, that's 100 divided by 78.12 for the benzene, plus our mystery compound, compound Z. We know how much we have, 8.05, so our number of moles would be 8.05 divided by Z, the molar mass. Okay, so now let's just do a little bit of math here. We can rearrange this, and we get 100 divided by 78.12 plus 8.05 divided by Z. That's equal to 100 divided by 78.12 divided by 0.948. We do that arithmetic, we get 1.3503. So really what we have here is that 8.05 divided by Z is 0.0702. We solve for Z, we get 114.64 grams per mole. So we've answered our question. Our questions were, what is the mole fraction of solute, which was, our answer was 0.052. What is the molar mass of compound Z? It's 114.64. All right, problem 2. How many grams of sucrose, table sugar, molecular weight, 342.3 grams per mole, must be dissolved in 320 grams of water at 25 degrees Celsius to lower the vapor pressure by 1.5 millimeters of mercury. The vapor pressure of water at 25 degrees C is 23.8. Well, that's not a very big drop in pressure. So let's see if we can figure this out. We're going to take the same approach as the previous problem. We know just one compound. So we know that chi of the solvent is going to be P of the solution divided by P of the solvent. We have both of those things, 22.3 and 23.8. Where did we get the 22.3? Well, that's 23.8 23.8 minus the 1.5 millimeter pressure drop. So they don't really give it to us directly. We have to calculate it. We have to recognize that that's a thing we could calculate. So 22.3 divided by 23.8, we get 0.937. And that means the mole fraction of the sucrose is 1 minus 0.937, or 0.063. Now, we could write the mole fraction equation of either of these, but it's probably going to be easier if we use water, because then we'll only have the unknown occur one time in the equation rather than twice. We could still solve it. It's just easier if we do it this way. So let's write that equation. The mole fraction, 0.937, is the mole fraction for the numerator, 320 divided by 18.02. That's water, and that makes sense because 0.937 is the mole fraction of water. divided by the number of moles of both compounds, water and sucrose. We have the first item, 320 divided by 1802, that's water, plus Z, the number of grams of sucrose, divided by its molar mass. We rearrange this equation. We do a little arithmetic. Well, okay, some algebra. And we get Z divided by 342.3 is 1.1945. Let me encourage you to stop this video, write out the equation, solve it for yourself, and make sure you get the same answer that I do. When we solve for Z, we get 408.9 grams of sucrose. So that's our answer. All right, next question, more of a multiple choice question. To calculate the freezing point depression of an ideal dilute solution of a single non-dissociating solute in a solvent, what's the minimum information we have to know? All right, let's go through this. Here's our formula to compute the change in freezing point, or otherwise known as the freezing point depression. It's our freezing point depression constant times the molality of the solute times I, the Van 't Hoff factor. That I value is 1 if it is non-ionic, if it is a non-dissociating covalent compound, which this is because the problem says it is. I is 1. So what do we need to know the freezing point depression? It looks like what we need is K and M. So that makes our answer choice B, just the molality and the freezing point constant. Now, it's not C because if we ask for the freezing point of the pure solvent, we could then calculate the new freezing point, which is great, except that's not what the question's asking. What's the boiling point change for a solution containing 0.328 moles of naphthalene, which is a non-volatile, non-ionizing compound, in 250 grams of liquid benzene, and they give us Kb for benzene. Naphthalene is a non-volatile, non-ionizing compound, so I is 1. So we know that our boiling point elevation problem, or equation, very similar to the freezing point depression, except we use Kb instead of Kf. So we want to solve for molality, moles solute, divided by kilograms of solvent. So 0.328 moles divided by 0.250 kilograms. We just took our number in grams, divided it by 1,000. We get 1.312 moles. Our delta T boiling then becomes our Kb times our molality, and I get 3.32 degrees Celsius. That is not my boiling point, that is my change in my boiling point, which is what this question is asking for. So the answer is A. All right, we'll save this last problem for a short third video, and that's all for this time.